Now we come to the last discussion topic of this week, returns to scale. So return to scale has to do with how output will change or will respond to a proportional increase of all inputs. So like increasing all inputs with the same factor. Now, does it sound familiar to you? Yeah, a little bit. So return to scale is something already interested since the time of Adam Smith, sometimes called the father of modern economics, right? And he observed what happened in a manufacturer or a factory where they produce pins. And what happens, the question is, what happens when they upscale the production with means increasing the input, all inputs, labor and capital at the same proportion. So we have to keep in mind two possibilities, two things might happen simultaneously when such an upscaling happens. The first thing is, okay, give you greater resource to specialize the production. So for example, if you have more labor, then you can have more divisions of production, and because of that, each division can specialize in a certain phase of production. That would mean a gain in efficiency, right? On the other hand, that will also exhibit a risk of loss in efficiency, because as production gets larger, may get more complicated in management and so. So the question that Adam Smith had in mind was, okay, what actually happen if we do upscale it? Which force, gain or loss, will win or will overtake the other? Okay, so let's go into the details of returns to scale. What does it say? So now, if you have a production function with two inputs, labor and capital, and then you multiply all inputs. Remember, must be all inputs, by the same positive constant. In this particular case, because we're talking about upscaling, then it must be, it would make sense to have a t larger than 1. Then, okay, the first case, you have constant return to scale when you multiply all the factor by t, then the output increases by t time. This is the output, right? This is called constant return to scale. For example, if you double input, double labor, double capital, you get double output. That's constant return to scale. Does it look familiar to you, this expression? Think about it for a minute. We go back to that. The second thing is the decreasing return to scale. So decreasing return to scale means that when you multiplied all inputs by the same factor t, you get less than t times the output. So for example, if you double the old input, but you'll get less than double output, that's decreasing. But intuitively, you should get something more, not less than the original output, right? We wouldn't do that as a firm owner. Okay. And then the last case is increasing return to scale, saying when you multiply all inputs by t, you get more than T times the output. Again, double all the input will give you more than twice the output as original production scale. So that's the idea. One thing to note is it is possible for a production function to exhibit constant returns to scale or any kind of return to scale for some level and then change to the other in other ranges. One case we had in the beginning was the qubit production function, right? When you increase in the beginning, output will increase rapidly, but like keep increasing, then it will slow down. All right, let's do some example. Let's derive or find out the return to scale for the Cobb-Douglas production function. So now that we have this production function, we multiply every, let's call it F, K, L. We multiply every input by a factor T larger than 1. What would we get? So F, TK, TL will equal A TK to the power alpha times TL to the power beta, right? And let's factor out the T, simplify it a bit to see what comes out of that. So we have A T times, T to the power of alpha plus beta, right? Then times K to the power of alpha as before, and L also to the power of beta as before, which is exactly T times, again to the power of alpha plus beta times F K L, right? The original production functions. So the thing that we had before. Now think about this. We have 3 cases. The first case when alpha plus beta equal 1. Then we have F, TK, TL equals. So if alpha beta equal 1, then T to the power 1 is T, right? Time F, K, L. And this is what's said by constant return to scale. Now, the second case, similar procedure. So if alpha plus beta smaller than 1, take it slowly. So if alpha and beta smaller than 1, then we take care of the T first. T to the power of alpha plus beta will be smaller than T. Actually here, T to the power of 1, right? As a result, F, T, K, T, L, which is this term, will be smaller than T, F, K, L, right? And therefore, we have decreasing return to scale. The last case, if we have alpha plus beta larger than 1, then we have t alpha to the power alpha plus beta will be larger than t to the power 1, right? That means the whole thing here, which is the f, tk, tl, will be larger than the t times f, k, l, right? Because here you have t to the power alpha plus beta times f, k, l, which is this part, this guy. That means we have increasing returns to scale. And this is a particular interesting property of the Cobb-Douglas production function, where you can tell from the return to scale already by looking at the exponent of the function. So the reason why I asked you if it's familiar, because we have seen it when we talk about the homogeneous function. So actually the definition of constant returns to scale coincides to the definition of homogeneous of degree 1 function. So if you multiply everything inside the function by a factor t larger than 0, in this case even larger than 1, you will get the result is t times the value of the original function. So t times output in this case. As a principle, when a function is homogeneous of degree k, its derivative are homogeneous of degree k minus 1. So in this case, the derivative of the production function is the marginal productivity, right? So these marginal productivity functions are homogeneous of degree 0. Now, what is the implication of homogeneous of degree 0? That means if you doubled or you multiplied all the input by the same factor t, you will leave the marginal productivity the same, remain unchanged like before, nothing changed. No? That's the definition of homogeneous of degree 0. And by that, we can see that the marginal productivity of any input depends only on the combination on the ratio of capital and labor. So the composite of the input and not on the scale of production. So if you keep upscale, 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 because of homogeneity of degree 0, that will not change the marginal productivity of input. Okay, remember, we talk about homothetic and homogeneous function in the beginning. So homothetic function is any monotonic transformation of homogeneous function, right? And monotonic transformation in turn is transformation that preserves the trade-off relationship among between the variables of the function, even when the absolute value or the scale of the function changes. Because of that, in this sense, the constant return to scale production function is homothetic. So it's homothetic in the way that the marginal productivity and in turn the marginal rate of technical substitution, which is basically just the ratio of the two marginal productivity, right? Depends only on this ratio of the input used. and not on the scale of the production, like we said in previous slide. So now if you draw array like this now through the origin now with K and L on two axes. Along such a line, the ratio between K and L will remain constant. Doesn't matter how far you go from the origin now. So the isoquants will equally spaced as the scale of production expands along this rate. Now, so the slope of the isoquants will remain the same in this point. They just shift along the line now. And the tangent line at this point will also have the same slope. This is quite abstract, but sometimes it will be useful. Okay, that's it for this week.